So in the last lecture, we have established canonical decomposition. But this was proved modulo 1 result, and that result is what we are going to prove today. So recall that for any state j, nj denotes the number of visits to the state j by the Markov chain, which is essentially this sum. Then what we have proved already is starting from j, expected value of nj will be finite when j is transient, and this will be infinite when j is recurrent. Because this expectation will just become the sum of the probabilities, and then we'll just use the criteria to get this. On the other hand, this proposition that we are going to prove today is the following. If j is transient, then we'll actually show that expectation starting from any I of nj is going to be finite, not just j. Okay? And hence, in particular, if expectation is finite, the random variable has to be finite with probability 1. Okay? On the other hand, if j is recurrent, then we'll show that for any I in S, probability starting from I of nj being infinity is just Fij. So therefore, as long as I leads to j, from I one can reach j, after that, nj being infinite is obvious because j is recurrent. So therefore, the probability, this probability is same as the probability that I will eventually lead to j. Starting from I, one can eventually reach j, and which is Fij. That's the idea. And of course, in particular, when I is equal to j, this will just give me, j being recurrent. Starting from j, the number of visits to j is infinite, has probability fjj, which is 1. Okay. So note that in the last class, the form of this proposition, we didn't have this expectation being finite. We just wrote it as this is finite, but we'll actually prove this, that the expectation is finite. Okay, so before proving, we'll actually first observe that how does it compare with the previous things. So if you look at 2 is definitely stronger than B. So 2 implies B for sure. It's actually stronger. That's because, this statement just means that this is infinite with positive probability perhaps, or even it can be finite, and then even the expectation can be infinite, right? So it doesn't say anything about what can you say. It doesn't say much about this probability. Okay. However, this is definitely stronger because we know that this probability is 1, and therefore expectation has to be infinity. This is a random variable that takes the value infinity with probability 1, and therefore this has to be infinity. On the other hand, as I said, the random variable may not even maybe finite with probability 1, and yet it may have infinite expectation. So therefore, definitely 2 is a stronger, much stronger statement than B. The 2 implies B in particular. On the other hand, 1 also is stronger than A because 1 takes care of this expectation starting from any state I, not necessarily J. So if you put I equal to J, the special case will give you A. Okay? So therefore, this proposition is definitely stronger than what we have already proved so far about these expectations. So before giving the proof, let's give one more application of this proposition. This is a very important result which comes out as a corollary of this proposition. So what is the corollary? The corollary is that if the state space is finite, then not all states are recurrent. In particular, this means when the state space is finite, there is at least one recurrent state. So therefore, if you have an irreducible Markov chain on a finite state space, then obviously at least one state being recurrent will immediately imply that all the states are recurrent. In particular, the Markov chain has to be a recurrent Markov chain. Later, we will actually show that all states of an irreducible finite space Markov chain are actually going to be positive recurrent. Okay, this is something we'll prove after covering stationary distribution and so on. Okay, so let's prove this application first. So we'll show that if the state space is finite, then all states, not all states are recurrent. Suppose S is 1 up to K and all states are transient. We'll arrive at a contradiction. Now fix a state I. Note that Nj is the sum. This is the number of visits to J. And hence, the expectation of Nj starting from I, okay, is just expectation of the sum, which is the sum of the expectations. Okay? Some expectation of a sum is sum of the expectations, and each expectation is actually a probability because expectation of an indicator is a probability. So this is the sum of these probabilities. Now, what is this probability? This is just Pijn, n-step transition probability. We know that from the proposition that since all states are recurrent, in particular J is recurrent, and therefore for every state J, this is going to be finite. This sum is going to be finite. This expectation is going to be finite. So that this is finite for every state J, this comes from the proposition. This is finite. On the other hand, we have shown that this is equal to this, so therefore this is also finite. So in this particular, this says that for all ij, this is summable. Okay, and hence, in particular, this goes to 0 as n goes to infinity. Now we'll use this to find a contradiction, to arrive at a contradiction. So therefore, first of all, this Pn is all P power n is also a transition matrix. So therefore, its row sum is going to be 1. This is the ith row sum. We have fixed an I. Is going to be 1. Now this is a finite sum. Each term is going to 0 as n goes to infinity. So therefore, the sum also goes to 0 as n goes to infinity, which is a contradiction because it's identically equal to 1. Okay? This sequence is identically equal to 1, but that converges to 0, which is a contradiction. And the contradiction has to come from the fact that we have assumed all states are transient. Therefore, at least there is one state which is right.